Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. Well, we've got a great topic for you today. It was by request. Here it is. What is a masked move operation? Looks kind of scary there with that masked man on the screen, but let me assure you it's not a scary topic. This one came in from my friend and colleague, Mr. Bill Rainier, who had used a masked move function in another PLC with a previous project, and he thought it was very useful, and he was looking to do something similar in Cscape, so he suggested the topic. Now, Bill, of course, since he suggested it, he knew exactly what a masked move was, but I didn't at the time until he explained it to me, and I'll be explaining it to you as well. All right, but we think you'll find it's a very useful feature. All right, now before I dive into that topic, I'm going to bring in our product manager, Mr. Casey Gardner. How are we doing today, Casey?
Hey, not bad. How's it going, Chuck?
Good. Now I have two questions for you. The first one may be more important than the second, but here's the first question. So, who is in honor of the masked man on our title today that Marcy Tyree put in there for us for a little bit of fun? Who is your favorite comic book or movie villain? Got to ask that.
Sure. In terms of I won't say I have a favorite. I'll go with the one that came to mind when you talk about a masked villain. Not necessarily a favorite by any means, but Doctor Doom was probably the first one that came to mind. So I'll say Doctor Doom to start with.
Very good, very good. Now keep in mind, from my side of things, I grew up in the, watching Batman reruns from the 60s TV show. So all those villains were pretty campy, and most of them wore masks, not all of them. But my favorite probably, and he didn't even wear a mask, I don't think, would be the Heath Ledger Joker from that Batman a few years ago. He was pretty awesome. Okay, now back to business. I'll have to ask you, do you know what a mask move is?
I don't. That was one of the first questions I had when we saw the topic. So looking forward to it.
There you go. So as I'm telling Casey and the rest of you what a mask move is and how to use it in Cscape and what it's good for, Casey will be standing by to answer any questions you may have in the chat section. If you're watching on replay, give us those comments and questions in the comment section, and we'll get to them just as soon as we can. All right, let's dive into today's topic. Okay, so here's how we're breaking down the topic. First of all, of course, what is a masked move? We're going to finally answer that question. We're also going to talk about bitwise operations. Now, we've covered bitwise operations before, but you'll see why we're covering them again today in a bit of a review. We're going to talk about the types of applications where you would use a masked move function, how you would code it in register-based advanced ladder, the classic style of ladder that still a lot of Horner customers are using. And then we're going to talk about doing a masked move using a user-defined function block in variable-based advanced ladder. So that's a little bit more capable, a little bit more modern version of our ladder logic in Cscape. And of course, we'll have plenty of demonstrations. All right, let's go ahead and dive right in. Okay, so finally, let's answer the question, what is a masked move? Well, a masked move operation is a move function where you are overriding only a portion of another variable. So let me give it to you like this. So, with a move function, you have a source and a destination, and the function of a move is to move the source data into the destination location. Well, with a masked move, you can move just a portion of the data and overwrite just a portion of the destination, leaving other parts of the destination variable or destination register untouched. So that's what a masked move is. Now, masked moves are considered bitwise style operations. What is a bitwise operation? Well, it's any operation or function block that operates on variables bit by bit. So AND, OR, XOR, those sorts of functions operate bit by bit. So those are bitwise operations. And a masked move would be considered a bitwise operations because it does operate on a bit by bit level when it does the move. Now, what are bitwise operations useful for? Well, they're often used for parsing data. In other words, taking a chunk of data and dividing it up into multiple variables. And they also can be used for the reverse, packing data, taking multiple pieces of data and packing it together as a single variable or data stream. Now, there are many applications where this is useful, and I've got a few of them on the screen. A lot of them have to do with communications. CAN-open in J1939, satellite communications, cellular communications, Modbus in some cases, barcode reading, RFID data, lighting control even, especially if you've got a lot of sequencing going with lighting. And what all these applications have in common is the need to efficiently utilize data in the smallest practical packet size. So the efficient packing of data, usually over a network, is what we're talking about, where a masked move and bitwise operations in general can be useful. Okay, so let's do a quick review of bitwise operations. Again, bitwise operations are a set of instructions in Cscape that perform on the bit patterns of the variables or registers that they're used with. So they operate bit by bit. And they're often used, again, to parse or mask off certain parts of a variable for the purposes of reading a portion of that variable and moving it into another storage location. Here's a real-world example, and we'll give you a real-world example using register-based advanced ladder. Okay, it works the same for both register and variable-based, but let's go with a register-based example. So let's say we have a variable, let's say it's stored in %R1, and let's say that is actually integer data that was read from a third-party Modbus device. So elsewhere in the OCS, we had a function that read data from a Modbus device, and we stored it locally as a 16-bit value in register %R1. Now, as it turns out, that 16 bits of data, within that 16 bits of data is 8 bits of data that we care about. And let's say in our example, those 8 bits are smack dab in the middle. Not the lower 8 bits, not the upper 8 bits, but the 8 bits in the middle. And maybe that's data we want to separate from the word and store as a separate piece of information. So to do that, we're going to use a couple of bitwise operations. The first thing we're going to do is to perform an AND function. And the second thing we'll do is a shift function. So let me go into a little bit more detail on that. So let's start with the AND function. What the AND function does is it's typically used to mask off bits from a variable that you don't care about. So in our example, okay, we've got those 16 bits at the bottom shown in yellow and red, and the bits we care about are the ones in red in the middle. So the way an AND function works is you take a variable, you AND it with a value, let's say a Boolean value, which is converted to decimal when it's input into Cscape, and that value represents a bit pattern. So in our case, with the AND function, when you're creating a mask, everywhere in your mask value where there's a 1, that bit will come through. Everywhere there's a 0, that bit will just turn into a 0 and be ignored. So in the end, you would put a 0 for your mask everywhere you see yellow X's on the graphic, and you would put a 1 everywhere you would see a red N. So you'd end up with a pattern of 4 zeros at the top, 4 zeros at the bottom, and 8 1s in the middle. And when you performed the AND function, you would get back the data in the middle. So in looking at it in a little more detail here, there's that original register at the top. There's our data mask with that pattern I talked about. Now, when we take that binary pattern and we convert it to decimal, we end up with 7698 in this exact example. Then when we perform the AND function, we get the data back that we care about, which is the 8 bits in the middle. Now, the problem, though, is we're not quite done, and that is because the data comes back and it's not sized properly. In other words, it's shifted up four positions higher, which means it is 16 times too great for the value that we're looking for. So we just need to perform a shift right or shift down 4 positions to get the data where we want it. So again, with bitwise operations, we can perform an AND and a shift, and almost always we can use that to extract the exact portion of data that we're interested in from a larger word of data where it's been carried in. Now, this approach works great for extracting data, which is what we've just done, but it doesn't work that well for injecting data. In other words, Let's say the data that we were extracting was speed feedback data. So maybe it's coming from a drive and it's telling us the relative speed of that drive from 0 to 255, because remember we had 8 bits of data there in the middle. So that was, we were extracting the speed feedback. But what if we were looking to inject a speed command very similarly, but this time we needed to write data instead of read? In that scenario, the AND and the shift that we just performed wouldn't work nearly as well. And I'll explain why now. Okay, so we have a similar but different situation. So now we want to write a speed command to a drive, and we're going to use a slightly different register number to hold the speed setting. Again, let's say it's an 8-bit speed setting from 0 to 255. Let's say that's stored in register 111, and that we need to take that data and pack it into register 101 and send it off to the drive. Let's say that's the goal of the application. So at the bottom there, you can see we're going to take our speed setting from 0 to 255, and we want to place it where you see the S's in R101, the 8 middle bits in that particular register. Okay, so what about just using the bitwise operations we just did? Why don't we do the shift first, okay, to move the data where it needs to be, and then why don't we do the AND after that to accomplish what we want? Well, unfortunately, that's not going to work, because an AND function or an OR function or an XOR function, they only have the capability to write to all the bits of the destination. So you can't tell that function which bits not to write. The result you will get is, yes, you'll get the speed data in the center where you want it, but the 4 bits on the end, top and bottom, will all be zeros, because the AND function has to write to every position. It cannot ignore positions. And that's where the masked move comes to the rescue. So with a masked move, you can specify a mask like you do with an AND function. But in the case of the masked move, that mask basically says, I'm going to move data to those positions, which are ones in the mask, and I'm going to leave alone or ignore the positions which are zeros in the mask. So you end up with the result you want, the speed data, in our example, right there in the middle, and we don't touch at all the 4 bits at the bottom or the 4 bits at the top, just because I've set the mask to only write to the middle 8 bits. So I've told you what a masked move is. I've told you where you could use it, how it's similar to the bitwise operation, and how bitwise operations don't quite work for injecting data, et cetera, but okay, how do you perform a masked move in Cscape? Well, first of all, Cscape does not specifically have a masked move instruction. That's why Bill wanted me to cover the topic. He wanted to know how to do that. But in Cscape, we do have the ability to access individual bits within variables, which is a very useful function. And that's where, especially if you're using register-based logic and even variable-based logic, you can utilize that capability with some Boolean logic and individually copy a bit from one variable into a bit from another variable. And you can select the source bit number and the destination bit number. So in our example, the way you would do that in Cscape, if you were using the traditional register-based approach especially, and you weren't using a user-defined function block, is for every bit you wanted to write from a source to a destination, you would need a rung of logic with a coil and a contact on it. So our example, we wrote 8 bits. That means 8 rungs of logic. So that's what we would do in that scenario. So not too difficult, but it does require a few simple rungs of logic to make that happen. Now, the advantages to this approach is it is pretty straightforward. Okay, it's also flexible. You can move a bit from any one variable to another variable, from any position to any position. So again, it's not difficult. You just have to know to do it. Something you may have not been familiar with, like Bill may not have been familiar with it. But there are some disadvantages to this approach as well. If you've got a lot of data to move, for every bit you want to move, you need a rung of logic. So it can, or at least it has the potential to be tedious. The other thing to be aware of is in variable-based advanced ladder, you don't have access to bits 17 to 32. So if you've got a double word that you're talking about, for words, it's no issue. But if you've got a double word variable that you'd like to do some sort of a masked move function with, you don't have access to the .17 to .32 bits, at least not in Cscape 9.9. Now, in Cscape 10, we've added that capability in, but it's not in 9.9 at this stage. And of course, as we record this, Cscape 10 is not quite yet available. Okay, so let's take a different approach then. Let's say instead of just writing a rung of logic for every bit we want to move, instead, let's say we created a user-defined function block instead. So what I have done is I have made two UDFBs available, one in integer form and another a double integer form, or more accurately, a word and a double word UDFB that allows you to perform the masked move, and more than likely, you'll be able to do that complete operation in a single rung, okay? Now, the advantage of that, of course, is you can do it in a single rung, and if you've only got a couple bits to move, you can still use the old approach of just using Boolean logic to move a bit from one word to a coil of another word. So that's not a big deal. You can mix and match as it makes sense. Also, there really aren't any disadvantages. Yes, you have to import the UDFB, which takes a couple minutes, but as long as you download it and import it, that's not really much of a disadvantage. Okay, so let's dive right into Cscape and our benchtop demonstration and take a look at what a masked move function block looks like. All right, let's fire up Cscape. Here we go. And so what we've got here is, this is my example that utilizes a masked move user-defined function block. So I'll show it to you here. It shows up in my toolbox under UDFB. So it's mask move word. So this is the 16-bit version. And just like we started to talk about, or we started to do, and that was, we said, okay, for this write that we want to do, let's say of speed control, let's shift the data over first, 4 positions, then let's do a AND function. Well, that wasn't going to work because the AND writes all the bits. But we would do a similar function here, except instead of an AND function, we would use the user-defined function block. So we do start by taking a speed variable, which is 16-bit variable, but the values are between 0 and 255, because that's what we're needing to control in the drive in our example. We're going to shift it over 4 bits, so we're shifting it up 4 bits, so it lines up with where we want it to be lined up when we actually do the masked move. Now we need to create a mask, and remember, a mask is that binary pattern where there are zeros everywhere we want to not perform the write, and ones everywhere we do perform the write. So that means 4 zeros at the top, 8 ones in the middle, and 4 zeros at the bottom. And when we convert that pattern over to decimal, and it ends up at 4080. So that's why we've set our mask at 4080. Okay, so here is our user-defined function block. Our first input is the data that we want to write, and that is our speed data shifted over 4 positions. The next input is the mask, in other words, the bit pattern that we want to write to, and that is our 4080, and I could have just typed that in as a constant here too. It doesn't have to be a variable. And then the next input, as well as the output, is where I've actually assigned the data that I want to write. So this is the variable that I want to write to in its original form, and this is a result of the masked move being written effectively to that same variable. So after I perform the masked move, I should result in having only my speed data written to the middle 8 bits, and the other bits should all be left alone. So let's check that out on the bench and see how that works. Okay, so here's my example program in action. I've just got a simple screen here for demonstration purposes. Here's my speed value from 0 to 255. For convenience purposes, I've shown kind of the binary pattern of that value, currently all zeros, of course. This is the word that is going to be written over the network, the theoretical transmit word 3 I'm going to send out over the network, where I need the middle 8 bits to be the speed, and I don't want to touch the top or the bottom 8 bits. So I have the ability in this demo here to set a bit pattern that we can remember. Okay, and so as I change speed, I want to make sure these bits on the end do not change, but that the value in the middle, this value right here, does. Okay, so let's go to 55. Here's our bit pattern. Here's our bit pattern. Nothing changed on the end. No matter how many times I change it, again, bit pattern matches. My speed successfully was injected into this word, but my other bits on the outside were not impacted at all. So definitely the result was what we were looking for. Okay, now before I move on and show you the double word version of this function block, let me just quickly show you the logic inside the function block. Now you don't need to know that. This is just for, interest purposes. You can see how I created the user-defined function block that performed this function. So let's go here to the logic for the user-defined function block and just take a look at how we did it. So it's very similar to what I talked about before, the fact you can take any bit from any variable and write it to any bit to another variable. The difference here with this user-defined function block is we have to be able to, it could be any of the 16 bits that need to be written. So what we have here is for every bit of output, and remember we've got, this is a word function, so we have 16 bits of output. For every bit of output, we have a single coil where we're going to either write it as a 1 or write it as a 0. Now, if the mask coming into the function for this bit, if it is a 1, we're going to copy over the bit from the first input. If the mask is a 0, it says we want to leave that alone. We don't really want to change the output bit at all. Then we take the second input, a value for that bit, and we just pass it through. So if it was already a 1, the bit will stay on. If it was already a 0, the bit will be off as it was before. Whereas if our mask is on, that bit position is a 1, then we're going to write instead the data that we want to transfer through. And we're just doing that for 16 bits for the 16 words. So that's what we've got here in the logic. So pretty straightforward. But again, you wouldn't want to have to do too much of this to do a mask move. Being able just to write this logic once or import this UDFB once and utilize that function block in an application where you're doing a lot of bit packing and a lot of those sorts of things can be pretty useful. All right, now let's go ahead and close this program. All right, so we're closing that program. I'm going to go ahead and now open up the D-word demo. And you're going to see it basically works the same, right? Except this time I'm using the same example, except everything is just twice as long. So I've got a 32-bit D word, which I need to pack with the middle 16 bits of data. And I want to ignore the lower 8 bits and the upper 8 bits of those 32-bit words. Now, I'm just putting the data in the middle in both my examples, but you could really put it anywhere. It doesn't just work if you put it in the middle. So the beauty of the masked move is you can do it wherever you need it. So same as before, we're taking our speed data, which this time is a 16-bit value between 0 and 65,535. We're taking that value, we're shifting it by 8 bits this time, because that's what our example is doing. Our mask is a lot larger because we have 8 zeros at the top, 16 ones in the center, and 8 zeros at the bottom. If you do the binary to decimal conversion, that's the number you get there. And then this is a 32-bit operation for this UDFB instead of 16 bits. So, you know, it's obviously doing the same thing, but just with double integer or word type variables. All right, let's go ahead and take a quick look at our bench again. First thing I'm going to do is load in my double word program. Okay, that's the advantage of using removable media. Look how fast that program is loading. Like a rocket ship, it was that fast. Okay, so this is the same similar example at least, but for double word instead. So again, speed is in the middle. That's the value I want to change. I have a bit pattern for the top 8 bits and the lower 8 bits that we're not going to change. We want to make sure those stay the same. Again, as I add in and change my speed, nothing changes at either end. Okay, even as I go all the way to 50,000, of course that number there changes, but the top and bottom bits are left unchanged. So worked all like a champ, as you would expect, and pretty simple to use as well. Okay, so before we wrap up and go to our wrap up, let me show you the logic inside of this function block, which is very similar to what I showed you before, but slightly different with a little bit of a trick in there that you might be interested in. Okay, so the logic for this guy starts out exactly the same. The first rungs for the first 16 bits are exactly the same, but we have to get a little clever when we get to the upper 16 bits, and that's because, again, with variable-based advanced ladder, we don't have access to bits 17 through 32 of a 32-bit variable. So what we need to do is we need to rotate by 16 positions all 4 variables, the 3 input variables, including the 2 inputs and the mask, and the output variable. And when we do that, now the words or the bits that were at the top are now at the bottom. The bits we just wrote to previously and the previous 16 rungs, that were at the bottom are now at the top. And now we can copy and paste the other 16 bits. Okay, and then when we're done with that, we do another rotate by 16 positions to get all the bits back in their original position. Now, of course, you don't have to do any of this. All you have to do is execute this simple rung of logic and perform this user-defined function block. So you can take effectively any double word source, decide which of the 32 bits you want to actually write, and then write those to that particular output variable. So nice and straightforward. Okay, let's go ahead and go to our wrap-up now. Okay, so industrial communications especially often involves packing communication packets with bits, bytes, and words as efficiently as we can, whether you're talking about communications over cellular or satellite, maybe communications that's doing some lighting sequencing, whatever the case may be. Standard move functions and standard bitwise operations, they typically write to the entire variable instead of just a portion of the variable. You know, byte, word, double word, whatever it happens to be, they're writing to that entire destination. Whereas a masked move will only write to the bits that you specify in the instruction, allowing the other bits to be unchanged. So this can perform what you're looking to perform without having to accidentally overwrite data that you don't want to overwrite. Okay, so I hope you found that interesting this week. This is where I remind you that we're here every Tuesday at 2 o'clock on YouTube, whether we're fully live like today, or whether we're pre-recorded because of a travel schedule or something. But in any case, we've always got somebody standing by as the video is shown for the first time on YouTube to answer your questions. For the live folks, it's in the chat section. For the replay folks, it's in the comment section. And in either case, we'll either answer you immediately or answer just as quick as we can. A reminder, we're celebrating 10 years of the Horner Lighting Group, and all their great videos are alongside the automation content on the Horner YouTube channel. Now, if you're interested in training, we've got basic OCS training and advanced OCS training coming up this summer. The dates are on the screen. Nate and Tim both do a tremendous job depending on who's training. I think it's Nate this time. So sign up for those. I believe there are still spots available. Now, next week, we're going to talk about a topic which is important for a lot of you, and that's string handling. So anybody who's ever done anything with, let's say, barcode readers, or with dealing with RFID data, or any other ASCII-based or string-based data, you're going to have a need to extract a portion of the string and store it in the location you're looking for. So it's similar to what we talked about today, but it's specifically all based around strings and ASCII characters. So you won't want to miss that. Okay, if you haven't subscribed to our channel, don't hesitate to do so. It doesn't cost anything. And if you choose notifications when you subscribe, you'll be notified every time we go live or every time we post a new video. Okay, so until next week, let's all get out there and do us some good.